Here we have a charger. The charger can be represented by an EMF, which is the ideal voltage. But also we have to include an internal resistor. And in this case, the question says its internal resistance is 0.2 ohm. So we represent the charger with a dotted line here. And this is actually when we measure the charger, the output at the terminals. This is what we measure from here to here. And R1 is the internal resistance. Now 15 volt should be put in here. R1 is 0.2 ohm. And the same apply to the car battery. The car battery has its own EMF. In this case, it's 1.5 volt. And its internal resistance is 0.05 ohm. So we use a dotted line to represent the car battery. So when we connect the charger against the car battery, we actually have two EMF, V1, V2. We also have two resistors, R1 and R2. Now, we want to find what is the current passing through this loop. You can see there's one single loop here. Now, let's look at KVL along this loop. KVL. And let's see. Now, the orange path represents the loop. We are going to analyze this circuit. First, we enter the V1 from the negative side. So the first term we should put is negative 15. And then we ask R1. Now, if you look at the two sides of the R1, here must be positive because the potential here must be higher than the potential here. So when we analyze using KVL, this loop, the orange one, enter R1 from the positive side. So we use the rule say because the path enter the R1 from the positive side, we put positive here. So this is positive. But remember, we need to put the voltage. It means the voltage across R1. So this should be the voltage across R1. But we don't know I. Therefore, we just say this, remember, equal to IR1. R1 is 0.2. So we just say 0.2 here. And we put the I here. The same argument, cross R2. This must be positive. This must be negative because we assume the current passing through along this direction, and also it enter V2 as well. This is how we charge the battery. So the same argument, positive. The voltage across R2 we don't know, but we can write in terms of the resistance, which is 0.05 multiply I. The current or the loop which we set up to analyze this circuit enter V2 from the positive side. So here we have to put positive 11.5, and this is KVL along this loop, and they must equal to 0. You simplify this one, you will get 0.25 I equal to 3.5, and I is equal to 14 ampere. Next, we want to find the terminal voltage across the charger. It means from here to here. This terminal voltage can be found from this argument. First, we have 15 volt across V1. So this is 15 volt, 0. And this voltage will drop because when it across R1, some of the energy will lose. So it means the V terminal at the charger is equal to 15 minus how much drop across R1. Of course, how much drop across R1? We can also apply this one is IR1. 15 minus, we just found I equal to 14 and R1 is 0.2. So the answer is 12.2 volt. So it means at the two terminals of the charger, it only provides 12.2 volt. So this is the charger. For the car battery, the EMF of the car battery is 11.5 minus I, how much drop across R2? R2, so 11.5 minus 14 times 0.05. And you will see this is equal to 10.8 volt. So this is what you can measure across the car battery at this moment is 10.8 volt only. This circuit has one voltage source, which is 10 volt. It also has a current source. It is 2 milliampere. We can see there are two nodes, A or B as well. So we focus first on node A. We want to set the KCL, it means Kirchhoff current rule applied to node A. Now, we can say if we assume the current from the 10 volt passing through the R1 enter node A, so we call this I1. We also can see the current source, which is 2 milliampere, will pass through R2, and this is I2. It also enter node A. We can assume the current I3 will flow out from the node A. So the KCL say current flowing into the node I1 plus I2 must equal to the current flowing out the loop. And we can say I1 plus 2M equal to I3. Now, I want to draw your attention here. I do not put A, the unit, here. I just put 2M. It means I put the numerical value and the prefix only to simplify the calculation. And of course, we'll put the unit at the final answer. So we can call this one equation 1. Next, it means part B. We need to apply KVL along E1, R1, and R3. E1, it means our voltage source. R1, this is R1. R3, it is R3. It means it is so clearly, it is the path along this. Okay. So again, if we analyze this one, first we start from the voltage source. This is negative and this is positive. So the path we enter the voltage source is negative. So because it entered from the negative side, so we should put 10 volt as negative 10 volt. Here, R1, we first put this is positive because the current I flow from the positive to the negative. R3, this must be positive. This must be negative. Okay, so let's analyze this one. KVL, and for the 10 volt source, it entered from the negative side, so it's negative 10 plus the voltage across R1. The voltage across R1 is I1 multiply R1. So R1 is 1K, and this is I1. So this is the voltage across R1. Plus, again, because the loop enter R3 from the positive side. So, but this time, passing through R3 is I3. So the voltage across R3 is bracket I3. And this is 2K. This is equal to 0. So this is equation 2. Now next is we want to solve I1 and I2. Now the procedure is like this. We first simplify number 1 first. So from number 1, this is part C. From number 1 will become I1 minus I3 equal to minus 2m. This is become 3. The way we usually write is, if this is unknown, I1, and write I3, we see we have 2 unknowns, so we put I1, I3, and then equal to the numerical value. And this is the way we can solve the equation. And this is very similar to the way we deal with the system of equation in X and Y when you were in high school. From 2, we can rearrange this, become 1K I1 plus 2K I3. And this is equal to 10. So this is equation 4. Now we can see equation 3 and 4. We have 2 equations, 2 unknowns, I1 and I3. And we see something here. We see that in equation 4, the coefficients 1K. And so what we can do is we multiply 3 by 1K. So equation 3 become 1K I1 minus 1K I3 and minus, now this is interesting, minus 2m multiply 1k. So we can see m here represent 10 to the minus 3, k represent 10 to the power 3. So when they multiply, they equal to 1. So it means the right hand side here is actually equal to 2. So we can simplify this one, 2. This is equation 5. Now, it means we try to solve 5 and 4. And 4 minus 5. If we do this one, we'll find this one is equal to 3ki3. And this is equal to 12. So I3 equal to 4 milliamp. Because remember, I3 is 12 over 3k. Because this is over 3k, 1 over 1000 is equal to 10 to the minus 3. It means we just say 4 10 to the minus 3. So it's very easy. 1 over k is m in terms of the prefix. The KCO say I1 plus I2 equal to I3. And we know I1 plus I2 is the current source, 2m equal to 4m. So it means I1 must equal to 2ma. So let's put down the value. I1 is 2ma, I2 2ma, I3 4ma. Part D, calculate the voltage or potential difference across R1, R2, and R3. V, R3, I3, R3, and this is 4m, 2k. Again, m and K will combine become 1. So this is 8 volt. V R2, I2, R2, and this is 2M, and this is 3K, and it becomes 6 volt. VR1, this is I1, R1, and this is 2M, 1K, and this is 2V. So if we along the loop, the first one here again is KVL. The first one is negative 10 plus the voltage across R1. Voltage across R1 is 2, so it's plus 2 volts plus the voltage across R3. R3 is positive 8 equal to 0. So the KVL correct. So we can also say because the potential drop across R1 is 2 volts, so the absolute potential here at point A or node A is equal to 10 minus 2. This is 8 volt. And if this is 0 volt, and also the voltage across R2 is 6 volt, so this is 6 volt. So it means now the voltage across the current source is 2 volts. Here is a potential divider. A voltage source, which is 12 volt, is connected in series with R1 and R2. In this particular example, R1 is 4K ohm and R2 is 8K ohm. Now, the potential across R1 and R2 is 12 volt. If you measure the voltage across R2, it means this one, and it will be lower than 12. Or the same, if you measure the voltage across R1, it also will be lower than 12. So our aim is to find what voltage we'll get. Let's call the voltage across R1 as VR1. This voltage will proportional to V in this case 12 volt, and the proportional constant is a fraction. The denominator is R1 plus R2. The numerator is R1. It means if we want to get the voltage across R1, the numerator is R1. So plug the number in. This is 4K plus 8K multiply 12, and you will get 4 volt. The voltage across R2, same, is proportional to V in. The proportional constant is a fraction. The denominator is R1 plus R2. But because you want to get the voltage across R2, so the numerator is R2. So this is 8K over 4K plus 8K. Multiply 12, you get 8 volt. Now you can see the sum of 4 volt and 8 volt is equal to 12 volt. So the 12 volt is the input, and with the R1 and R2 connected in series, it divides the 12 volt into 4 volt and 8 volt. The higher the value of the resistor, the higher the voltage you will get. This circuit is a current divider, a current source which produces 15 milliampere of current. The current flows through until it reaches the node here, and it splits into 2 branches. Branch 1, it passes through R1, and R1 is 30 ohm. The second branch, it passes through R2, which is 60 ohm. we join at the other node and return back to the source. So this is called current divider. It means it divides this current into two branches, and R1 and R2, they are connected in parallel. So let's look at what is I1 and what is I2. First, I1 is clearly proportional to I total, and the proportional constant here, again, it is a fraction. The denominator is R1 plus R2. However, the numerator is R2. It means it is the R2 here tells you how much current passing through R1. So if we plug here, R2 is 60 over 30 plus 60 times 15 milliamp, and you will get 10 milliamp. I2, again, it is proportional to I total. The proportional constant is a fraction. Denominator R1 plus R2. Numerator is R1. So it is R1 control how much current passing through the R2. And if you plug this one in, 1 is equal to 30. 30 plus, okay, and you will get this is times 50 milliamp, and this is 5 milliamp. So again, this is 15 milliamp. I1 is 10 milliamp. I2 is 5 milliamp. So the sum of I1 and I2, they must equal to 15. And also it makes sense because I1 is passing through a low resistance. So this is 30 ohm, therefore the current is higher. I2 passes through R2, which is higher, its resistance. So the current will be 5 milliamp, it means it's lower. So in the parallel circuit, because they have the same voltage, the higher the resistance, the lower the current. Here we have a potential divider. The input voltage is 12 volts. R1, it is 4k ohm. R2, 8k ohm. If we want to get the voltage across R2, we can apply the formula. Say the voltage across R2 is equal to 12 multiply the proportional constant, which is a fraction. The denominator is 4k plus 8k. The numerator is AK, because AK is the R2 where we try to get the voltage from. Now, if you plug this one into your calculator, you will get 8 volt. However, if we really want to get 8 volt, we must connect this circuit to an external load. It means we are actually connected our load in parallel with the R2. Now what happens is effectively you change the resistance. So we have to first calculate what is the parallel resistance, and this is the R2 parallel to the R load if you connected your load across the R2. And if you plug this one into the calculator, you will find this is equal to 8k ohm parallel if our load is 4k ohm, 4k ohm. And you will find this is equal to 2.67 k ohm. So effectively, you have a circuit like this, plus minus 12 volt. The R1 doesn't change, which is still 4k ohm, but instead of R2, you get the R parallel, and it becomes 2.67 k ohm. So you can see, compared with 8, 2.67 is lower. So you can imagine the voltage you get from here, if you really measure, will be lower. So how much you really get? This is V parallel proportional to 12, proportional constant. This time, this fraction is 4k plus 2.67k, and the numerator is 2.67k. And if you plug this number in your calculator, you will find this is 4.8 volt. So instead of 8 volt, which you would expect, but if you connect this one with a load which itself is 4k ohm, you will find you only get 4.8. It is substantially lower than the one you hope to get, which is 8 volt. In this example, we want to use a strain gauge in a Wheatstone bridge. And from here, we want to measure the force. Now, what is the Wheatstone bridge? Usually, the Wheatstone bridge is drawn like this. This is V in, and then if we draw it like this, this is R1, R2, R3, R4. And this is A point, B point. And from here, this is V, A, B. Now, a better way to see this one is, actually, you can look at it as two potential divider. So these two circuits, they are equivalent. R1, R2, R3, R4. So this is VAB. Because this point here is the same as this point and this point. So we can measure the voltage at this point. We can express the voltage at this point, and then we can find the voltage between A and B. R1, R2, R3, R4, A, B. This is VAB. So this is V in. So let's look at it. R1, R2, R3, and R4. R4 is our strain gauge, which is resistance can change if the force applied to this gauge change. So without any force, R4 equal to 120 ohm, and R1 120, R2 120 ohm, R3 120 ohm. So we expect the voltage across A and B should be 0, but let's prove it. So this is A, the initial voltage. The initial voltage, VA, proportional to V in is 10. And this is R1, R2, R2. And this is 120 plus 120 plus this is numerator 120 times 10. So you will get 5.0 volt. Same as VB, R4, R3 plus R4 times 10. So that's 120, 120 plus 120 times 10 and equal to 5.0 volt. So we call VAB VB, some people call it differential output voltage. So this is the voltage of A minus the voltage of B. So this is 5.0 volt minus 5.0 volt and equal to 0 volt. So when there's a no force changing the resistance of R4, you will get 0 volt. Now part B is if a heavy truck driving through the bridge, so it will change the resistance of R4 and increase it from 120 to 120.6 ohms. So R4 will increase to 120.6 ohm, very little. And let's see in this new condition, what is the voltage across A and B. So under the same condition, we'll say VA, of course, it won't change. It's still equal to 120 plus 120 times 10 equal to 5.0 volt. Whereas VB, this time, the denominator become 120 plus 120.6. And the numerator is R4, 120.6 times 10. So in this case, we'll get 5.01247 volts. So the voltage between VA and VB, it means the V out, which is VA minus VB, should equal to 5.0 volt minus 5.01247 volt, and you will get minus 12.47 millivolt. So you can see the resistance of R4 change from 120 ohm to 120.6 ohm. It means 0.6 over 120 is roughly about 0.5%. Now this change in resistance caused 12.47 millivolt change. And with the modern equipment, it's very easy to measure 12.47 millivolt change. In this question, we have 12.6 volt car battery. This is the EMF of the battery. And it has an internal resistance of 0.02 ohm. When it starts, it will take 150 ampere, huge current. So we can draw this one as this. This is your EMF, and then we connect the EMF with a internal resistance. So this is R, this is the EMF. With the dotted line, we represent this is our battery. And at this point, and at this point, the voltage across here is the terminal voltage. It means this is the voltage we measure with the meter. When we connect this one to outside, this is our load. So itself, it is a potential divider. Start, it will take 150 ampere. So I equal to 150 ampere. Part 1, it asks what is the voltage drop internally as heat inside the battery. It means the voltage drop across the internal resistance. So we know the I, we know the R. So A, the V across the internal resistance, we call the internal, is equal to I, internal resistance, R. So this is equal to 150 times 0.02. and you will get 3.0 volt. So here you got 3.0 volt drop across the internal resistance B. So what's the terminal voltage actually get when you start? This terminal voltage here is equal to the EMF minus what you drop internally. So the EMF is 12.6 volt. What it will drop across the internal resistance is 3.0 volt. So you will get 9.6 volt. It means when you start your car, your machine, you get 9.6 volt instead of 12.6 volt.